isomorphisms. So an isomorphism is when there is a one-to-one correspondence between the vertices of the two graphs G and G prime, and there's a one-to-one correspondence between the edges of two graphs G and G prime. So if this is graph G and this is G prime, what we want to do is show that that there is this vertices on this graph G has an association or can be mapped to the different vertices here in the W's. So let's take a look. So if I look at vertex 1, it's got degree 4. So coming over here, can we see a vertex here that would have degree 4? Yeah, I see that W2 has degree 4. So V1 goes to W2. All right, let's look at V2. So V2 is connected to that degree 4 vertex, but it by itself only has a degree 2. So thinking about this, so this degree 4 at W2, we want to find the vertex that has degree 2 that's associated with it. So I could do either W3 or W4. So it's doesn't necessarily have to be unique mapping. So I'll make that one go there. And then let's look at V3. So V3 is over here. It has degree 3. So degree 3 vertex, that would be one of these two, a W1 or a W5, right? So I'll just go with W1. Then the V4 has a vertex of degree 3. So that's going to be one of these two. And since I've already done W1, I'm going to go to W5. And then V5 is here, and it's connected to the degree 4, but it has degree 2, and so that will be the W4. Okay, so if there's just vertices labeled and no edges, you'd be done, but this also has edges labeled, so we need to go figure out how the edges map to each other. So looking at E1, so E1, where is E1? I think I meant to say E1 is up here. Yes, I think so. So E1 is this one right here. E1, okay. So it's going to have an edge that goes from a vertex of degree 4 to a vertex of degree 3. So vertex of degree 4 to vertex of degree 3, I could choose either F3 or F7. So I'm going to go with F3. Then edge 2 would be here. So it's between two vertices of degree 3. And so that would be either F1 or F2. So I'll just pick F1. Then E3. E3 here again is between two vertices of degree 3. So that means E3 should be F2. Okay, so we've got these ones taken care of. So let's look at E4. So E4 goes between a vertex of degree 4 to a vertex of degree 3. So that looks like it would be degree 4 to degree 3. I've already used F3. So how about F7? F7 down here. Then E5. Where's E5? E5 goes between a vertex of degree 4 to a vertex of degree 2. So that would be a vertex of degree 4 to vertex of degree 2. So I can choose either one of these two, right? So I'm just going to go with the 4. Then E6 here is the vertex between an edge between two vertices, each of degree 2. So that'll be the 5. And then the last one is here. So this is an isomorphism. Okay, if there's an invariant, if there's something that stops it from being isomorphic, then, if there is an item that stops it from being isomorphic, we call that an invariant. And so here are some of the invariant possibilities. So one graph has n vertices, another graph has a different number of vertices. So these are the things that you want to check. Do they have the same number of vertices? Do they have the same number of edges? Is there a vertex of a certain degree? Or are there 3 vertices of degree 3? Does it have a circuit of a certain length? Both of them? Connected, Euler circuit, Hamilton circuit, all the things. Okay, so let's look at this G and G prime. So looking at it, so I'm just going to start with counting the vertices, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, it's got the same number of vertices, and you don't have to go through this whole list, but I'm just going to, for sake of just counting everything. So 1, 2, 3, 4, 5, 6, 7, 8 edges. And then this graph has 1, 2, 3, 4, 5, 6, 7, 8 edges. And let's see, a vertex of degree K. All right, so this vertex here has degree 4, right? Is there a vertex here with degree 4? There is not. So there's a degree 4 vertex here and not here. So that's the invariant. And you could find other ones also. All right, so let's look at this graph, H and H prime. So again, I'm just going to start with the vertices. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same number of vertices. 1, 2, 3, 4, 5, 6 edges. 1, 2, 3, 4, 5, 6. Oh, 7 edges. So 7 edges, 6 edges. So there it is. We have the invariant.